Today we're going to be taking notes on Unit 10.2, and this will be Part 1 of Fields at Work. We will be discussing potential and potential energy. We will be discussing field strength as well as potential gradient and potential difference. Let's begin. Remember from Unit 5.1, we discussed the electric field between two charged plates. We learned that the electric field could be measured as the change in potential divided by the change in distance. We call this potential gradient. We can now show that this result is correct. In the diagram here, there is a positive charge that has a size Q in a field between two charged plates. This is negative and this is a positively charged plate. The field strength is E and the force F acts on that charge so that F equals EQ. From 5.1 Part 2, we learned that the potential, V, is equal to the work done in a moving charge, which is W, divided by the magnitude of the charge, Q. When we solve for work, we have work equals V divided by Q. We also know that work is equal to a force that is applied over some distance x. When we set these equal to each other, we have V divided by Q equals EQ times x. The Q's would cancel out, and we get left with V equaling E times D. When we solve for E, we get E equals V divided by D, and we also know that the electric field strength is equivalent to F divided by Q. So therefore, we have this equation here, which is E equaling V divided by D and equaling F divided by Q. So this pretty much just shows us how electric field strength can be written and calculated in two different ways. The first way is that the electric field can equal the potential, which is V, divided by the distance, which will result in Newton per coulombs. And the second way to calculate electric field strength is by dividing the force by the magnitude of the charge, which will result in volts per meter. Let's do an example. A pair of parallel plates with a potential difference between them of 5.0 kilovolts are separated by 120 millimeters. Calculate the electric field strength between the plates and the electric force acting on a doubly ionized oxygen ion between the plates. Go ahead and try this and then start the video back up. Okay, so we're going to be using this equation here. We plug in all of our information, so we have 5,000 volts for the potential. We have, for the distance, 0.12, and that is in meters, and we get an answer of 4.2 times 10 to the fourth volts per meter, and that is the electric field strength. For part B, we know that the charge of the ion is 2E, and the reason why we want to do 2 times the charge, because we have a doubly ionized oxygen ion. So we take the charge, which is 1.602 times 10 to the negative 19th coulombs, times 2, equaling a positive charge of 3.2 times 10 to the 19th coulombs. Then we want to eventually figure out the force, so we take the equation F equals QE, and we plug everything in, and we get an answer of 1.34 times 10 to the 14th newtons. When looking at a charged plate, we can find the amount of charge per given amount of space, which we call surface charge density, and this is denoted by a lowercase sigma. Surface charge density, the density of the area, is the Q, which is the charge, divided by A, which is the area. There is one equation that deals with the electric field strength and the surface charge density on two charged plates. If you are asked to do a problem that involves this, the equation will be given to you. The equation is Q equals epsilon naught times VA divided by D. From taking this equation here that we are given, we know that Q divided by A is the surface charge density. So if we move A over here, we get Q divided by A equals epsilon naught V divided by D. We also know that V divided by D is the electric field strength. So if we substituted E for V divided by D, and we substituted Q divided by A for sigma, then what we get is sigma equals epsilon naught times E. If we solved for E in order to know what the electric field strength would be, then we would get sigma divided by epsilon naught. Because this equation is for the field between two parallel plates, each plate accounts for half the field. So we need to adjust by 1/2. And when we do that, we get the final equation, which is electric field strength, E, equaling sigma, which is the surface charge density, divided by 2 times epsilon naught. Look at the diagram up top with two charged parallel plates. The electric field created by the charged plates is uniform, so E is the same here. Notice the positive charge located between the plates, and this is a positive test charge. The left charged plate is negatively charged, and the charged plate to the right is positively charged. The potential difference is marked from 0 to 12 volts. As you can see in the potential versus distance graph down here, this graph shows that as the positive test charge moves further from the 0-volt plate, the potential increases. Next, take a look at the electric field strength versus distance graph. Because the charge is moving within an electric field that is uniform, the electric field strength is the same. So, as the positive test charge moves closer to the positively charged plate, which is this direction over here, then the field strength experienced will be the same, and therefore you have a linear graph. Now, when talking about graphs, we can talk about the gradient or the slope. The gradient of the potential distance graph from over here is known as the potential gradient. Potential gradient is the change in potential divided by the change in distance, or d. This is V divided by d. We can then make the connection that the electrical field is the negative potential gradient, or the negative sign of delta V divided by delta R replacing the variable d for distance. The minus sign just lets us know that the direction of the vector electric field is always opposite the potential. So looking at this diagram on the left, we can see that the vector going from positive to negative, which is from right to left, if the test charge moves from the negative end over here towards the positive end, the charge would experience a gain in potential. For example, if we moved the test charge from 12 volts to 0 volts, the change in potential would be 0 volts minus 12 volts, and remember we carry this little negative out here, and that would give us a positive 12 volt gain in potential. This tells us that the motion is in the direction of the field. If the charge moves from 0 to 12 volts, then we put this in, and we know this is our final, this is our initial. When we solve for that, we get a negative 12 volts, or a loss in potential. This tells us that the charge is moving opposite of the field. Here is an example. Two parallel metal plates have a potential difference between them of 1500 volts and are separated by 0.25 meters. Calculate the electric field strength between the plates. Go ahead and try this and then start the video back up. Okay, so we're going to be using this equation here, and when we plug everything in, notice how we are already given the potential difference, and it is positive. So we don't have to do anything with this negative out here because it is already given to us in the positive form. So when we plug everything in, we get a positive 1500 volts divided by 0.25 meters, and that gives us a total of 6 kilovolts per meters, or you can also do kilonewtons per coulomb. Either one would be fine in the units of measurement. There are many connections made between our units. Many units do not stand alone in concepts or the equations. When we discuss potential differences in fields with charges, there is another concept where fields come into play. Remembering back to our circular motion unit, we discussed gravity and how an object's mass determined the amount of gravity that it has. Remember that gravitational fields exist for all objects with mass. The difference between field lines with charges and field lines with gravity is that charges can be either positive or negative, and depending on the charge, the direction of the field will either be inward, as seen here with the negative charge, or outward with positive charges. Gravitational field lines, on the other hand, are always directed inward towards the center of the object because there is attraction between all objects of mass. Objects with mass have gravitational fields, which are attractive forces, and there is an equation that determines the gravitational field strength, which is quite similar to the electric field strengths. The equation for gravitational field strength is G equals the negative delta V sub G divided by delta R, where G is the gravitational field strength, and V sub G is the gravitational potential, and R is the distance. Now, remember how finding the area under a force distance graph gives you the work done to move an object over some distance r? Well, we can find the amount of work done to move an electron some amount of distance by finding the area under the graph of an electric force distance graph. The electric field strength versus distance graph, if we find the area under the graph, this is the potential change of a single point positive charge. Here is a graph that shows the electric field strength versus the distance for a single point positive charge. This incorporates the inverse square law, which is why we're able to see a parabola for the shape of the graph. The area under the graph at points R1 and R2 show the potential change. The area under the graph here at R3 shows the potential at R3 to infinity. The area under the graph of an electric field strength versus distance is equal to the work done per unit charge or the change in potential. Since energy needed is the same as work done for a charge, we should be able to calculate this value by using force times distance. The potential, or V, of an electric field is V sub E for charge equaling K times Q divided by R. How did we get this? We know that F equals K times the charge 1 times charge 2 divided by R squared. And we also know that work equals force times some amount of distance. So we get W equals K times charge 1 times charge 2 divided by R squared times R, and the R's would cross out and we're left with K charge 1 times charge 2 divided by R. Now we also know that work equals charge times the potential. When we set those two equations together, then we get VQ equals K times Q1 times Q2 divided by R. The Q's would cancel and we would be left with the potential of a charge equaling K times Q divided by R. And that's how we get this equation. The potential can also be found within a gravitational field. Gravitational potential is known as the work done in bringing a mass from infinity to that point. It can also mean the potential energy of a mass placed somewhere within the field. The variation of potential against distance r for a mass m is shown in figure 1 and is given by the equation V sub g equaling the negative g times m divided by r, where g is the gravitational constant, m is the mass, and r is the distance of the point mass. Since the gravitational field is attractive, there is a negative amount of work done to bring an object closer to the Earth. Therefore, the gravitational potential energy is always a negative number when using this reference point. Close to the surface of the Earth, the gravitational field is fairly constant. The gravitational potential, therefore, increases steadily as the distance above the ground increases, as seen in this picture. Potential energy of an electric field is by definition the charge times the potential. This is given by the first portion of the equation E sub P, equaling Q times V sub E. Sub E meaning charge. It also means the energy a charge has that is due to its position relative to other charges. The potential energy then is also equal to K times charge 1 times charge 2 divided by r, which is the distance. By separating the two charges to a radius r, you are giving the charges electric potential energy relative to each other. When you release those charges, they will attract or repel, releasing that energy. Opposite charges will attract, just like Earth and an object with gravity. Like charges will repel. The gravitational potential energy of a mass m, is the energy required to bring the mass m from infinity to a point on the field. It can be calculated by simply multiplying the gravitational potential at that point by the mass m. The first part of the equation then is E sub p equaling m times v sub g. Gravitational potential energy also refers to a mass m, so the gravitational energy at a point in the field distance r from the center of the mass that is producing the field is negative g times m, 1, so mass of one object, and the mass of the second object, divided by r. Here the forces are always attractive for gravity, and thus there is always a negative with a maximum of 0 at infinity. Here is an example. Two parallel metal plates have a potential difference between them of 1500 volts and are separated by 0.25 meters. Calculate the electric field strength between the plates. Go ahead and stop the video and start this back up when you're ready. Alright, so we're going to be using this equation here, and we have E equaling V divided by R. And when we plug in everything, we get an answer of 6,000 volts per meter, or 6 kilovolts per meter. Here is another example to try. What is the gravitational potential energy of the moon with respect to the Earth? The mass of the moon is 7.35 times 10 to the 22 kilograms, and the mass of the Earth is 5.98 times 10 to the 24th kilograms. The Earth-Moon distance is 384,400 kilometers. We'll be using this equation here, and when we plug everything in, our units cancel out and we're left with a total of negative 7.63 times 10 to the 28th joules, or you can also put it into megajoules. We have talked about point charges and parallel plates. Let's focus now on a hollow conducting charged sphere. A conducting sphere has the charge on the outside of the sphere, as seen here. Here we have a negatively charged sphere. We know that the field strength inside the hollow sphere is 0. How is this mathematically proven? Looking at this figure, there is a test charge that is placed inside the sphere. The test charge could be placed anywhere within the sphere and it would work out to be the same. The distance from the test charge to the sphere is Rs for the small cone, and S being for small, and then RL would be for the large cone. Looking at this data table, we know that the area of the end of the cone for the small cone is pi x sub s squared, and for the large cone it is pi x sub l squared. The charge on the end of the cone that is for the small cone is sigma pi x sub s squared, and for the large cone it is sigma pi x sub l squared. The distance we already know as being r, and we gave that as r sub s and r sub l for the small and the large cones. Given this equation that we already know, that is force equaling K times charge 1 times charge 2 divided by r squared, because we know that the charge, which is Q, equals sigma pi x sub s squared, we can just put this into this equation here to get the force on the test charge due to the area of a charged sphere. So we would get the force on the test charge due to the area as being K times charge 1 times this right here, which is sigma pi x sub s squared, all divided by r sub s squared. For the large cone, the force on the test charge due to the area would be K times charge 1 times sigma pi x sub l squared divided by r sub l squared. We know that using trigonometry, that these two cones are complementary. Therefore, we can then put the two forces equal to each other. And when we plug in the appropriate data points, the forces cancel each other out. So here we have the force for the small cone, we have the force for the large cone. If we were to place these two equal to each other and put in the correct data points, the forces would cancel each other out and we would get a net force of 0 within the sphere. Okay, we've reached the end of our TNOTES, and here are a few problems for you to do. Here is the first one, and here is the second and third one. Be ready to have this information ready to use in class.